Yes. Survey says yes. Yeah, okay. So we have a conceptual idea about how to combine resistors if they're in series or if they're in parallel. And the same caveat that I applied to capacitors also applies to resistors. If you go to a manufacturer and you say, I need 13 kilo ohm resistor, they will look at you and say, I'm sorry, you either get 10 kilo ohms or 20 kilo ohms. We don't make 13. And so the same idea applies that if you need some sort of resistance for some reason, you might have to combine resistors in series and parallel to get the equivalent resistance that you actually want. Manufacturers do not produce an infinite range of these things. They're set values, and then you design your circuit based on the set values that they provide. Unless you're something like Apple, right? If you're Apple, you say, I gotta make 10 million iPhones, and I need a 13 kilo ohm resistor, and then sometimes manufacturers will say, okay, we'll do it, right? Because it's a volume thing at that point. And also, for example, Apple wants to use one resistor, not 10, because that allows you to make the thing smaller, that makes the phone smaller, more compact, and makes it look all aesthetically pleasing. Anyway, okay, so that's all I have to say about that. But it would be nice to figure out some way to deal with a more general case. And that is essentially what we'll use for today's lecture, for Friday's lecture, and that should be enough to get you moving on the homework for Wednesday. And so the general case generally falls into what we call Kirchhoffs laws. Yeah, okay, I think I got that spelled right. There's like years that I only had like a single H, and there's something wrong there, and I think I got it corrected now, which, you know, to my shame, right? When you have a spelling mistake of a proper name for years on your slides. So Kirchhoffs laws. And probably the thing that makes me the most miffed about Kirchhoffs laws is that he states the stinking obvious. I am sharing screen. He states the obvious. The idea is twofold. There are two Kirchhoffs laws. Recording has started. I am sharing a screen. There are two Kirchhoffs laws, and the first one is essentially this. When you have a junction in the circuit, the water that goes into that junction has to be the water that comes out. Now, of course, we don't think of water in terms of a circuit. We think of charge, current. So one of Kirchhoff's laws, this is sometimes called Kirchhoff's current law, or Kirchhoff's, current law, KCL, Kirchhoff's current law, okay, is that the water in equals the water out. Or if you have a junction in a circuit, the current that flows into the junction has to be the current that flows out. Which is the idea that I was on Monday, and I completely ignored it, which means I went down that huge 15-minute rabbit hole about how not to do a problem. So like I said, it kind of missed me because he's basically saying charge is conserved. And you go to Kirchhoff and you say, well, yeah, of course charge is conserved. You know, like, why do you get some fancy law named after you for stating the obvious? Because all the low-hanging fruit has been picked, right? Like, you no longer get to state the obvious and get something named after you. Life goes on. So Kirchhoff's law, charge is conserved. Anywhere where you see a branch in the junction, you know the current flowing in has to equal the current flowing out. If that were not the case, then charge would be disappearing somewhere. If you put more current into a junction than what comes out, there's some charge missing. It's disappearing into oblivion, which is a nay-nay. You're not allowed to do that. Second law. Man, I am just struggling today. I mean, I know there's days where I struggle, but like stuff is turning off on me. There we go. Second law. So I just drawn up here an equipotential map. It turns out this is a dipole. Okay? The arrangement does not matter. Okay? I just, conceptual purposes only, so don't feel like you have to write this down. I mean, like the dipole map or anything. But the question is this: if I have some charge that's represented by this green thing in a field, and so there's an electric field going on here, and I move that charge all over the place, and I end up back at the same spot. What's the change in potential? Okay, good. That's Kirchhoff's second law. Kirchhoff's second voltage law basically says, if you start at one location, go all the way around the circuit, and end up at the same location, your change in electric potential is zero. Or if you, conversely, if you want to think about it, you could say, if I start at the same location, I travel all the way around oblivion, and I end up back at the same location, the change in energy is zero. So Kirchhoff's first law is a statement that charge is conserved. You say, well, yeah. His second law is basically energy is conserved. You say, well, yeah. And those are Kirchhoff's two laws. Kirchhoff's two laws are charge is conserved, energy is conserved. Now, granted, he expresses it in terms of a circuit. So he says current in is equal to current out. And the second law we usually call the loop rule. If you start at a location on the circuit, you complete a full loop of the circuit, your change in electric potential is zero. You start at a position, you go all the way around the circuit and end up at the same position, your electric potential is zero. Stinks. No? I don't know. I don't know if PhD is in your school or in your future or not, but you kind of get angry sometimes when you look at a PhD thesis that's like 20 pages. You're like, really? Come on. And they still get their PhD. Then you look at yours and it's like 350 pages, and you're like, well, heck, I should get like 5. Right? It's just unfair. Life is unfair. Okay. Questions so far? So that's conceptually what we do. When we want to analyze a circuit, Kirchhoff's laws will help us do that. It will help us write down a series of equations that can be used to analyze a circuit. So bear in mind the underlying idea: charge is conserved, energy is conserved. Oh, junction rule. Yes, excuse me. Sometimes it's called the junction rule. You'll sometimes see it abbreviated as KCL or KCL because we're lazy. The loop rule is this. So if you go all the way around a circuit, the change in potential is zero. You'll also sometimes see this abbreviated as KVL. Kirchhoff's voltage law, Kirchhoff's current law. Now, a different way to say this, you could say, hey, as you go around the loop, your change in potential is zero. The other way to say it is, as you go around the loop, you might go up in electric potential. So somewhere else in the loop, you must go back down. So if you go up in potential at some point, you must go back down in potential somewhere else. So sometimes instead of seeing it written as V loop, you might see it as, and I'll put a summation sign in here, you might see it as, well, the sum of the drops equals the sum of the jumps. If I'm traversing through a circuit and I go up to the first floor, I must have to go back down to the ground floor somewhere else. Or maybe I go up to the first floor, I walk around for a while, I go up to the second floor, but then to get back to my original position, I've got to go back downstairs to the ground floor at some point. Okay. So at the risk of making this too algorithmic, this allows you, these two laws give you a way of approaching what's called a resistive circuit. If you have a circuit with resistors and batteries in them, and incidentally, this could be more than one battery as well. So you can have multiple resistors, you can have multiple batteries. Kirchhoff's current law, Kirchhoff's voltage law will allow you to go through and analyze the entire circuit. I should be more specific. It will allow you to find the currents flowing in all of the branches. So assume that you know the batteries, you know the resistors, Kirchhoff's current laws, Kirchhoff's voltage law will allow you to find all of the currents running through the circuit, which generally tends to be the case. You have the resistors, you have the batteries, you want to know the currents. So again, at the risk of making this too algorithmic, let me walk you through the process that I use. Now you might use slightly different process if you want. Okay, that's fine. Personalize your learning. Right? This is how Greg approaches it. If that doesn't work for you, find a different way to approach it. Okay, that makes sense to you. So how I start off with this is, first of all, draw the circuit. You don't necessarily have to use the drawing of the circuit that's provided for you. You are allowed to make the perfect wires as long or as short as you want. So if you don't like an arrangement that you see, go ahead and redraw it. The thing that you have to keep in mind when you do the redrawing is make sure that if your elements are in series, they stay in series when you redraw it. If you have your circuit elements in parallel, they stay in parallel when you redraw it. That's the one thing. So for example, I should ask, are these resistors in series or in parallel? They are in parallel, right? To go through one means that I do not have to go through the other. So you could redraw this circuit to your heart's content so it makes sense to you. Make sure those two resistors are still in parallel. And the resistor combination, I'll go a little bit further. Both of those resistors, the entire combination, is it in series or in parallel with the battery? It's in series. So the two resistors are in parallel with each other, and that combination of resistors is in series with the battery. As long as you keep those two characteristics the same, you can redraw the rest of this however you want. Sometimes it helps to only redraw parts of the circuit. That's fine. Just make sure you don't change the electrical connections. It would be another way of saying that. Okay, so draw the circuit. Next step, and this is again Greg. Go through and label the currents. Now, I would say that this is probably the most, I would say that this is probably the most conceptually taxing part, and I say conceptually. Okay? Because one of the temptations is to put more currents than you actually need. The temptation will be, so every wire that I see, I should put a current in. So for example, actually maybe I should have you do this. Go ahead. Thinking about all of the wires that you see here, you have one battery, you have two resistors. Go ahead and label currents in this diagram. Go ahead, talk to your neighbor, label currents in this diagram, and then ask yourself, do I have all of the currents? And do I have a sufficient number of currents, and do I make sure that you don't have too many currents? And so you need to have all of them, but you don't want to have too many. Okay. So go ahead, talk to your neighbor, see, go ahead. Start there. take a minute, label the currents. English is beyond me today. Maybe in French. Nobody understands French, right? Vous parlez français? Vraiment? Comment allez-vous aujourd'hui? No, 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 no.
How do they say no, I don't speak it?
Je parle pas le français.
Je parle français.
Je ne parle pas le français.
Je ne
Pas le français.
parle français.
Oui. Or, je parle l'anglais.
Je parle anglais or
L'anglais.
English?
Yeah. Yeah. No? Quoi? Sorry, I couldn't.
That's what I learned in the second one.
Yeah. One is the negation, one is I don't speak French, the other one is I speak English. So negation requires an extra 2 words in French, so ne and then pas, and you put the verb in the middle. Yeah. So parler is to speak. So the conjugated form par, it's hard to say in English, but you take off the R. So instead of parler, it's par. Je parle le français. There. Okay, you got it? Survey says, how many currents? Who says 1? 2? 3? 4? 5? And that's okay. That's part of the reason I want you to draw it. Okay. So it's good. I think everybody got a sufficient number, right? Nobody said 1 or 2. The question is do I need 4 or 5? Or is 3 sufficient? Like, okay, I'll go with the majority. 3 is sufficient, necessary and sufficient. The question is, well, where could you accidentally think that there might be more? Okay. So somebody, give me 1. Give me 1 of the currents that you said. Okay, this is 1 of the currents.
There's one going into
Okay, which resistor? Or do you mean?
your total current going into.
Oh, okay. So you have 1 current that travels along this branch. Okay, I see. So it travels along this branch and goes in right here. Okay. So let's see. What do we want to call that? I will call that I0, I0. Okay. Now you don't have to follow the same convention. What I try to do, this is again very personally. I usually I have resistor 1 up here, so I'll say that current 1 goes through resistor 1. Or I'll say that current 2, oh shoot, I just gave away, oh shoot, well that's one of Greg's. Okay, so Greg will do something like this. You could say, okay, well, I have a current 1 here. Where's another current? The second resistor. Now Greg's convention will be, I will call this I2. That's just so that when I'm writing down stuff in terms of variables, that sometimes helps me not make mistakes. Okay, so I agree. We have 1 current going from the battery into the junction right here. We have a current that anywhere else. The one that goes back to the battery, right? These 2 currents come through. There's another junction right here, and we have a 4th current.
Wouldn't I0, I4 technically be the same, so you don't really have a 4th current?
Good. And that's the warning. Because there is no junction, and that's also why I asked the question. Okay? Because I guarantee you at some point, you will find yourself making this mistake. If it wasn't right now, you'll make it later. And I say this because I've made the mistake. Not to say, well, I know you guys are better than me. Okay, there's no question about that. But I know that you'll make this mistake nonetheless. Because I don't care how good of a physicist you are, you're going to make this mistake at some point. And everybody I know has made this mistake. Right? So the issue is that right here, once I get here, you notice this whole path there is no place for me to siphon off some of the current. The battery doesn't siphon off the current, like the current stays the same as you go all the way through this entire branch, meaning that what we have labeled as I naught is the same thing as I4. The next question, you say, well, why does this matter? Why is it so important that I get the number of currents correct? We're trying to solve for the currents. If I have 4 unknowns, how many equations do I need? 4, right? If I have 1 unknown, I need 1 equation in order to solve for that unknown. If I have 4 unknowns, I need to get 4 equations to solve for the unknowns. So now here's 2 things. Number 1, you've added an extra current, which means now you have to find an extra equation. That's the first thing. So you've made your life harder. The second thing is, it will be one of those, do you guys remember every once in a while you get a redundant equation? Have you ever heard that term before? A redundant equation. Generally, it's you write down a bunch of equations, you start subbing and solving, and this probably happened to you somewhere. You start subbing and solving, and you get an equation that says 0 equals 0, or 1 equals 1. When that happens, if you have a series of equations, you start subbing and solving, and you get something that says 0 equals 0, generally that means you had a redundant equation. You actually had the same equation written twice. It might look different, but it's the same equation. Let me give you an example. If I wrote down something that said this, and this is very contrived, right? I'm not going very deep here. But if I said something like, okay, I have this equation, 2y equals 3x plus 1. Okay. And then I wrote down a second equation that said y is equal to 3 halves x plus 1 half. And then I tried to sub and solve. You'll get 0 equals 0. And if I take this and I try to sub that in for y right here, it looks like you have 2 equations, but if I sub it in, I'm going to get 0 equals 0. Now that, that's very highly contrived, right? You just say, oh, great, you just divide both sides by 2. They will not look that close together. They won't look that similar. Okay. But the same idea still holds. If you end up having too many currents on your figure, you will end up writing down a redundant equation somewhere. And so you'll go through all this effort to sub and solve, you'll get 0 equals 0, and you'll say, wait a minute, I've done something. You won't think I've got a redundant equation. I guarantee you what you'll think is, I've made a mistake in the math. And then you'll spend more time going through the math, convincing yourself you got it right, and you'll still end up with 0 equals 0. And then you'll come to Greg or Ty, and they'll go through it, and they'll get 0 equals 0. At which point, Greg will say, you've got a redundant equation. Hopefully, Greg doesn't do that. Hopefully, Greg looks at it and says, I4 shouldn't belong there. You just made your life difficult. So that's my warning to you. Don't feel bad if it happens. It will happen at some point. Make sure it happens like once, so you've already got it out of the way out. Right, yeah. Make $50 mistakes, not $1,000 mistakes. Make a mistake that'll cost you 5 minutes of time, not 2 hours worth of time. So good, okay, so let's get rid of this. Let's get rid of that. There we go. So we only have 3 currents that we have to worry about. And so the next question is, okay, yeah. So it's always good to remind yourself when you write these 3 currents in, or however many currents, just remind yourself, okay, I've got 3, I need 3 equations. I've got 5 currents, I need 5 equations. I have 10 equations, 10 currents, I need 10 equations. Okay. Yeah, no, I'm not going to make you do 10 equations, right? Once you kind of get a feel, maybe 3, maybe 4 just to see. But once you kind of get a feel for how to do it, then you can write down all the equations and the rest of it's just algebra. I say just algebra. I mean, it might take you an hour, but you have the... So once you get this down, you could expand it out to as large of a circuit as you want. And you've got the concept that expands, you can generalize it to a large circuit and the approach stays the same.
Wait, so how would current look like again?
I'm sorry?
Wait, so how would each equation look like? Like how would each equation look like in this example?
Haven't gotten there yet. Yeah, we're just doing the setup. Yeah. Yep. Okay, so here's the next trick. Okay. You have to choose a direction for the currents. Okay. So I just automatically drew in directions. I just put arrows in. Sometimes the direction of the current will be self-evident. Put that in. Okay. What that means is sometimes you can look at the battery, the way that the battery is put into the circuit, and have a very intuitive idea about which direction the current's flowing. Okay. Go ahead, write it down like that. If it's not evident, if it's not apparent, say if I have 3 batteries in the circuit, it might not be apparent which way the current is flowing in each of the branches. Choose a direction and stick with it. Okay. I'm going to say that again. Choose a direction and stick with it through the entire problem. If you choose a direction and stick with it through the entire problem, you will get the correct magnitude. If you get a negative sign in front of the magnitude, it means you chose the wrong direction. It should be going the opposite way. That's fine. Do the whole problem, choose a direction, stick with it through the entire problem, solve the entire circuit, and then at the end you say, that current's negative, that means it's going the opposite direction and everything's fine. So as long as you choose a direction and you stay consistent through the whole problem, you will get the right answer. The danger is you get halfway through, you find a negative sign, you say, oh, this current should go the opposite way. So you erase it on the figure, you draw it in the proper direction, and fail to take into account the other equations you have written down. That's why I say, just solve the entire thing and then worry about directions at the very end. So based on the directions that I have chosen, the next thing I would tell you to do is label the highs and lows. What I mean by that is based on the arbitrary directions I've chosen for the currents, label the high potential side of every circuit element, label the low potential side of every circuit element. So for example, let me do this in something like purple, just to try to get some sort of contrast here. Purple. Not going to give us very much contrast, but long bar on the battery. What does the long bar on the battery represent? The high potential side or the low potential side? The high potential side. So what I would tend to do is put a positive sign in here. I just tend to put positive and negatives. Again, referring to the potentials, not the charges. So I put a high and a low here. Next question, let's go up to resistor 1. I have chosen current to flow through this resistor going from left to right. Okay. Right up here, I've chosen it to go from left to right. Which side of the resistor is at the higher potential? The left, good. Current, you can think of current as being a positive charge. If the charge is going from left to right, that means that this side must be the high potential side, this is the low potential side. That positive charge will always roll downhill. So this is the high potential side, the low potential side. And similarly for R2, we've got the high potential side and the low potential side. I go through it, again, this is how Greg approaches it. I go through and I do this for every circuit element. So if there's 10 resistors, I choose the directions, and then I go through and label, based on the directions I chose for the current, what's the high potential side and the low potential side. So that's what I mean by label highs and lows. Next up. Again, remind yourself number of unknowns. Do this once when you write down the currents. Do this again when you get ready to write down the equations. You should check yourself like 3 times. Do I really need this number? Is it too many? Is it not enough? If you get that number wrong, then you'll spend too much time just trying to get equations to work out. So here we have 3 equations, or 3 unknowns. We need 3 equations. Now is the time that we will apply Kirchhoff's laws to write down our 3 equations. I find that Kirchhoff's current law is easier to write down and easier to manipulate. So I try to use Kirchhoff's current law to get as many of those 3 equations as I can. So my recommendation is start off with Kirchhoff's junction rule, the current rule. The idea that the current going into a junction is the same going out. Oh, I should ask that. How many junctions do I have in this circuit? How many places do I have where current can split? We have 2. One of them I have circled here. Here is one junction, and here is the second in boxes. However many junctions you have, you can write down one less equation. So I have 2 junctions here. I can only apply Kirchhoff's current law once. And you can sort of see that. If I do this left junction, what should I write down? What is the current going into that junction? What do we call that current? I naught. And going out is I1 and I2. That's if I write for this left junction. Well, let's go over to the right junction over here. And what would I write? Well, the incoming current, the current coming in is I1 plus I2, and the current exiting that junction is I0. Again, I've analyzed 2 different junctions, but have this, the same equation. Now, again, it might not be so evident sometimes. It might not be immediately apparent or as straightforward as this example. Okay? But however many junctions you have, you can use exactly one less equation with the junction rule. So if you find yourself with a circuit that has 8 junctions, you can use the junction rule 7 times. Good so far? I can't remember. Hopefully, let's get that out of the way. I think I typed it up very correctly. Hopefully, yeah, there we go. It's also nice to be self-consistent with the labeling, because I type it up and then I draw it up and then, okay. It just happens to match. All right. So what do? We have one equation using the junction rule. We need 3 in total, which means now I have to go to the loop rule. So how I apply the loop rule is I think about picking a starting location. So let me get these boxes out of the way. Pick a starting location on your circuit. Where would you like to start? You want to, okay. You want to start right here? Is that what you're thinking? Okay, there's no wrong answer. You're fine. Yeah. Okay, so let's start on the plot. We're going to start right here. And literally, usually I just put an X right there. Okay, so now let's pretend that we're at this location. We are going to walk around a circuit. We're going to walk around a loop so that we arrive at the same location. And just like I took that little dot and I just, okay. So we're gonna walk. Now this is a perfect wire. I'm going along the perfect wire. Nothing should, I don't have to worry about anything. Since the wire is perfect, there is no change in the potential. And I keep going, Okay, right here. I hit an intersection, I have to choose. Which way do you want to go? There is no wrong answer. Which way do you want to go? Up, okay. So we'll go up. I'm walking through. Now I'm forced to go this way, right? Why am I'm forced to go that way? Because this is the direction that I chose the current to go. Right? I naught tells me that the current must be going from left to right in this section of the wire. So I'm going to go this way, I'll go this way. Boom, I'm back at the same spot. I have just completed a full loop. So now let's apply the loop rule to write down the equation. So as I walk along, and I went across resistor 1. Was that a jump in potential or a drop in potential? It was a jump. Oh wait, did I say? Go ahead. Say it again. You said drop, and then I heard jump, and I say jump, and then I go, wait a minute, you're wrong. So I mishear, and then I tell you you're wrong.
Sure.
No, you're right. You're perfect. Right, this is the entire point of putting the plus and minus signs on. Is so that when you're tired and you haven't had enough coffee, I have to say, I find something terribly depressing when I get my toothbrush out in the morning to brush my teeth, and it's still wet from the night before. Do you guys find that disappointing? Has that ever happened to you? No?
What are you talking about?
I'm talking about like when I go to bed at night, I brush my teeth and I put it on the bathroom sill or whatever, and I go to bed and I wake up and I walk in after I eat my breakfast to brush my teeth and the toothbrush is still wet.
I thought you were saying the teeth were still.
No, the toothbrush. And I always get disappointed when that happens. I can't help it. Because that means that I was up so late that my toothbrush didn't have enough time to dry off before I had to get up in the morning. Which makes me sad. That happened to me this morning last night. I couldn't sleep for some reason, so. Sad. No, you've never noticed this? Don't start, it'll make you depressed. Okay, so yes, as we cross R1, we have a drop in potential. So what I'll do is I'll put V drop on this side. I'll put V jump on this side. And so when I crossed R1, I had a drop. So I'm going to put the change in potential across resistor 1. I'll just write that over here. Keep going. I keep walking. I hit the battery. Do I increase in potential or decrease in potential? I increase, right? The whole idea, again, of the minus and plus signs is that will tell you, are you going up in potential or going down in potential? So I go from a negative sign to a positive sign, that's a jump. And so I should put V battery over here. And now notice I'm back at the original location that I started at. I have now completed the entire loop. This tells me that the potential drop across resistor 1 should equal the potential jump across the battery. Next question. How do I relate the potential drop across the resistor to the current? How do I relate a potential drop across the resistor to a current? Resistance, yeah. Ohm's law. Ohm's law tells us, what can I write instead of delta V? Ohm's law tells us the drop across the resistor is equal to the resistance times the current through that resistor. So instead of writing this delta VR1, I can instead write the current through the resistor times the resistance equals the potential across the battery. I now have equation 2. Right here we have equation 1. Here is equation 2. That is a terrible one. Yes.
So what if the two resistors have different resistance?
No problem. If the two resistors have a different resistance, what can you tell me about the current through those two resistors? Different or the same?
Different.
They're different. And they will be different in such a way that they both have the same potential drop. In fact, this arrangement is sometimes referred to as a current divider. It will take the current and divide it through the two resistors, I'll say proportionally. Proportionally according to the resistance of the circuit, yada, yada, yada. To be continued. Quick, what other, we still need one more. We're one shy. Quick, write down another equation, go. Choose a loop, walk around it, get the jumps and the drops, go. Do I have it recorded? Oh yeah, I do. Just like paranoid that I'll forget to hit the record. Someday, Microsoft will set it up so when you start a Teams meeting, it records automatically. Someday, when you start a meeting, it will automatically download the attendance list. Little things. Much better one. You got it? You got one? Go ahead, tell me, what loop did you choose? Somebody, there's two more loops you could use. Just need to do one, but there's two more that you could choose. Okay, so you said, okay, well, I'll do the same sort of loop. I'll start here at the X, and I'll go around, but instead of going through resistor 1, I'll go through resistor 2, and then come back and start, okay? And what's your equation look like for that? Okay, right now, I'll put it up here. Delta VR2, the drop across resistor 2, equals V battery, the jump across the battery. And again, we can apply Ohm's law and rewrite this as the current 2 through R2 equals V bat. Which goes to Isaiah's point. If the battery is the same and the resistors are different, the currents have to be different. Yes?
Does going through the full path with the resistance count the base resistivity of the wire?
I'm sorry?
Would the resistance also count the resistivity of the wire?
We are counting the wires as being perfect. In other words, zero resistance. Now, that is a good point. What happens if you want to take the actual resistance of the wire into account? Model it as a perfect wire with a resistor in it, where the resistor value is equal to the resistance of the entire wire. Does that make, yeah. Mm-hmm. Right, a physical wire is just a perfect wire with a resistor on it. Physics is officially over. I mean, not the class, but in approaching this problem, physics is now done. You have three equations. You have this Kirchhoff's junction rule. You have two more equations from the loop rule. You can go ahead, sub and solve, and get your answers. Did everybody choose that as the second loop, just out of curiosity? Okay, I was just curious. You see where the third loop is? Instead of going through the battery, you could have just chosen this, right here. And then the interesting thing is you notice that the drop across R2 will equal the jump across the drop across R1 will equal the jump across R2. So the nice thing is that it doesn't matter which loop you choose. If you use that loop instead, you'll still get the right answers after you hack through all of the algebra. The danger is that you don't need all 4 equations. You only need 3. I'll get rid of that. Okay. So now we have our ugly mess. Let's get rid of some of this, get rid of that. And we're done. Physics is now over. We have applied conservation of charge. We've applied conservation of energy. We now have our 3 equations. All that's left to do is sub and solve. I don't know what your personal flavor is, but you know, let's just go at it. But I mean, immediately I see, hey, let's solve equation 2 for I1. Let's solve equation 3 for I2, and then we'll sub both of them into our current equation and get the value of I naught. And once you have the value of I naught, then you can, you know, back sub and do all, you know. I don't know, do you need me to do that, or do you just?
So you sub I1 for I naught minus I2.
I'm sorry?
So are you saying that we could sub in I1 for I naught minus I2?
Yeah, well, what I was thinking is, if you take equation 2 down here, you could write that I1 is equal to the battery potential over R1. And equation 3 up here in the upper right corner, you could write a similar expression, I2 is equal to the battery potential over R2. And then you could take both of those expressions and substitute it into equation 1 to find I naught. But what you said, if you wanted to say I1 is equal to I naught minus I2 and then substitute it in somewhere else, that's just as valid. Yeah. I mean, it's a fielder's choice at this point. You've got 3 equations, sub and solve as you see fit to get the expressions. Incidentally, those rules of combining resistors in parallel pops out here. In fact, you can see it. Okay, let me just write one more thing and then I'll promise I won't actually go through the rest of it. But you can see it, you have I naught is equal to the potential of the battery divided by R1 plus the potential of the battery divided by R2. You see that I have those 2 resistors in parallel and I'm doing some summation of them in inverse, which looks a lot like those rules for combining resistors in parallel. Indeed, it's the exact rule. The same thing will happen if you end up with them in series and you apply Kirchhoffs rules. You'll end up seeing, okay, those resistors in series just add together. And keep going. So those 2 rules are embedded in Kirchhoffs laws. Or maybe those shortcut rules come directly from Kirchhoffs laws. Might be a better way of saying that. Man, I should have put an empty slide in there, sorry. My guess is that I actually wrote down a couple of the loop equations as well. And questions so far? Yes.
So for the loop, we drew through both resistors.
Like this.
Yeah. So does that mean current can, because we drew current going to the right in both ways, does that mean it can go like the opposite way to one of them?
Yeah. So this circle I'm drawing in blue is just to help remind me the direction that I'm walking. Okay. So it's not to represent the currents. that are actually physically going through the circuit. It's to represent conceptually the direction I'm walking around the loop. Now, what physically represents the current direction are the highs and lows, the plus and minus signs the plus and minus signs that I put in. Okay. And how that comes in or manifests itself when I do the loop rule is that if I go from minus to plus, I'm going the opposite direction of the current. And so I get a jump in the potential. Yeah. Does that answer your question? Yeah. So I just drew this in not to represent the current, but rather conceptually which way I'm walking, so that it'll tell me if I do a jump or a drop. Yeah. Now again, if you stay consistent with your labeling on the figure, then you'll get the right values at the end of the day for the currents. And if you get a negative sign in front of one of the currents, it just meant that when you arbitrarily chose the current direction, you happened to get it wrong. You had a 50-50 shot, you got it wrong. That's okay. As long as you know how to interpret that negative sign at the end of the day, that's fine. It doesn't matter that you arbitrarily chose the wrong direction. And in fact, I think I'll have to double check, but I think like when I ask you for a current, I ask for the magnitude of the current. So as long, either I label the directions of the current for you on the figure, or I ask for the magnitude of the current. So that's very clear that, okay, if you arbitrarily chose the wrong direction, you should still get the right answer. Or I just say, here's the direction so you don't have to worry about it. I think, okay, yeah, I put some of that. Okay, there we go. Let's get all this gap out of the way. So I did actually write it in there. There you go. So I just wrote down all three possibilities. Okay. So of the three loops, these are the three equations that get generated. And of course, you only need two of them. And so once you get the two, you say, okay, I don't need to worry about that third one, right? Get rid of that and just start subbing and solving. This. So, I mean, again, I hate to, at the risk of making it sound too algorithmic, that's essentially it. Right? Like, I mean, physics is done right when you hit this point, and the rest of it is just algebra. Incidentally, I don't know, do you guys take linear algebra? I mean, I don't know for sure. If you ever have an opportunity to take linear algebra, you develop mathematical techniques to solve systems of equations like this. So it's okay, so I'd argue again, once you kind of have this approach, it really doesn't matter how big of a circuit I give you. Right? Once you have this approach, it could have 10,000 resistors. You say, okay, let me write down, let me figure out how many currents I need. Let me take into account all of the junctions. Let me do a bunch of loops. And okay, now I've got enough equations. Now I just run, like Charlie Brown. Right? Now, of course, that run like Charlie Brown, you might have 5,000 loop rule equations that you have to sub and solve. Linear algebra will develop techniques to solve those equations in a time-efficient manner. So you don't just have to manually sub and solve. There's some faster ways of doing it. Yeah. So if you ever have an opportunity, it's an interesting field. It's supposed to help make your life easier. Of course, you could argue that calculus was invented to help make Newton's life easier. Right? Oh, this physics problem is so hard, I don't want to have to do the infinite summation. I'll just invent this new branch of mathematics called calculus, and now it's easy to do it. No, maybe. Right? That's why calculus is invented, to help them do physics. Okay, I can see. You're protesting. You're saying, hey, Leibniz did it. Okay, I gotcha. Good, touche. Okay. Right? German mathematician Leibniz developed calculus at the same time that Newton did. Independent verification is very nice. Right? Two people working on separate ideas end up with the same conclusion. Okay. So again, you can make the circuit as complicated as you want at this point. So I should ask, for example, let's see here. Well, you know, I feel like I might have lied to you at some point. Oh, okay, I know. How many different circuit or currents do I have here? Good question. Yeah, talk to you and figure it out. How many independent currents do I have here? How many separate currents do I need to worry about? Let's see here. Okay. Yeah. Okay, I'll buy it. How many currents? How many different currents will be in through the solution? I agree with the answer you gave.
Okay.
Yeah. Oh, what's your question?
I was making sure that
Current path. Yeah, so the resistor is a single path, there's no junction. Although that's a good point. Yeah. Please bear in mind, resistors. Yeah, please bear in mind, resistors do not remove charge from the circuit. Resistors remove energy from the circuit. So that again kind of goes into this, be careful about how, your currents. So the second temptation, so we already talked about one temptation is to think that this current, which I previously labeled I naught, is different than this current, the current leaving the circuit over here on the right-hand side. The temptation is to label those as separate currents. They're the same. The second temptation, similar idea. The second temptation, which is a similar idea, is to think, for example, that you have a current running through 5, resistor 5, and right here you have a different current, I6, for example. That would be the other temptation. I say, oh, nay. If I look at resistor 5, if I enter resistor 5, there is nowhere else for me to go but to exit resistor 5. There is no junction, there is no separate path for me to follow. If I enter resistor 5, I have to exit resistor 5. Which means the current flowing through resistor 5 is the same as the current flowing through resistor 6. So I should not have two separate currents in this lower branch. I should just have one. Similarly, the middle branch, single current. Incidentally, this lower branch, that's that pipe question, right? You have a pipe that has a current flowing in one side, how much current comes out the other side? The answer is there is no junction, there's nowhere else for the current to go except to exit. The current going in has to be the same as the current coming out. So how many independent currents do I have? If I want to solve this thing completely, how many different currents do I have? 6, I agree. So what would I'd probably call this one, let's choose the wrong direction on purpose, right? You say, hey, Greg, the battery, so we'll just choose the wrong direction. That's fine, you can do that. It's perfect, it'll all work out. Okay. So I naught, I've got I5, I2. Just to let you know my other convention, if I have, multiple resistors along a single path, I tend to label the current corresponding to the lowest number. So that's why I called this current I2, because it goes through the second resistor. That's, again, just me. If you have, you can do it a different way, that's fine. I just wanted to let you know how I tend to do it. So you have I2, I5, yeah, you have a third one that comes up here, I1. Then you have I7, you have I8. So how many is that? 6? Yeah, that's 6. Be careful. This is one place where we have to be very careful. How many junctions do I actually have? So I've drawn it one way, but it's good to ask yourself, how many junctions do I actually have?
You have 4.
Good. I have 4. Or do I have 3? And this one comes in, and I'll say perfect wires are free. And I didn't think about it until I saw this one. I was like, oh, I need to mention the junctions. Yeah. I agree. When I looked at it just a second ago, I said 4. And then I said, uh-oh, I gotta be careful, and that's why I even mentioned the problem. Show you. I think we all agree this one's 1. I think we can all agree that this one is a second one. The question is this 2 separate junctions, or is that just 1 junction? That's just 1. That's why I say perfect wires are free. Imagine taking this wire right here, that segment, and shrinking it down to nothing. And then the junction will no longer look like 2 separate ones, but rather it will be, your 3 wires coming in, and then your 2 wires coming out. So you have to be careful. That junction, essentially the reason why you can say it's a single junction, there's no circuit element between the 2 points, the 2 connection points. You can shrink that perfect wire down to nothing and put all 5 wires connecting at a single location. So I can apply, I've got 6 unknowns. I can apply Kirchhoff's current law twice. And then the other 4 equations, I've got to do the loop rule. We'll pick up there on Friday. We'll get some more examples. So, hey, thanks for your attention.